Welcome to Sencox Technologies. Get ready for a simple yet effective comparison breakdown of three of the most common types of linear heat detection sensors on the market today. From digital to analog to fiber optics, we're going to explain each sensor's strength and weakness, as well as tell you what you should be aware of before making a safety-focused decision for you and your business. In our experience, the most common type of sensor in the industrial space is a digital linear heat sensor. It's primarily made of two steel conductors, heat-sensitive polymers encasing the steel conductors, a protective clear tape to surround the heat sensor polymer casing, and an outer jacket covering the full length of the sensor with all its previously mentioned components neatly tucked away inside. Some benefits of these types of sensor applications is that it's usually the most affordable on the market, as well as the fact that you can easily find and purchase these sensors from a variety of manufacturers with only a few clicks of your keyboard. We admit these common sensor types do have their uses, but when it comes to the volatile nature of most industrial safety operations, there are a couple of downfalls with this application's approach to safety. Firstly, when the sensor is triggered, it can't be used again, even if the outer jacket isn't damaged. This one-and-done type of configuration will no longer alert you in the case of reignition, nor in the more disastrous possibility of a complete fire outbreak. Another issue posed by these sensors is that there is usually no real-time monitoring capabilities. Whether it's a simple hotspot or full-blown fire, the sensor will only say there is a breach in both cases. So finding out how bad and exactly where this breach is coming from is all up to you to figure out. But the lack of real-time monitoring and temperature positioning aside, these sensors are known to create false alarms due to factors such as sunlight and abrasion, which for industrial industries is just part of a regular Tuesday. The last biggest downfall of the digital sensor is the issue of alarms and pre-alarms. Due to the limitations of the sensor, the assigned alarm can only be triggered when reaching a small window of set temperatures, such as 85 degrees Celsius. Because there is no pre-alarm capability, the alarm won't be triggered below or above the set alarm value, meaning that before the set alarm goes off, you and your staff would have no way of knowing that a breach is imminent. And in the case of an impending major issue, you wouldn't be able to tell, nor the time to spare, to shut down, clear out, or call in top-tier emergency measures by the time the set alarm goes off. The damage is done, and it's just too late. The analog linear heat sensor tries to address some downfalls of the digital linear heat sensor. With a sensor body consisting of one or two twisting pairs of metallic wires, NTC insulation, and an outer jacket to cover the length of the sensor. Some benefits to these types of sensor applications are that they are reusable if they were not damaged with temperatures higher than their set limit, and they are usually made of sturdier materials than what fiber optic sensors are made of. But there are still a few downfalls with this application when used in the industrial space. These sensors are usually made of materials that are very sensitive to environmental conditions, such as moisture and sunlight. Another issue is with the bending radius of the sensor body. Because of this sensor's materials, if you try to bend the sensor even a little too far or treat it a little too roughly, it will give a false alarm. And because of all the before-mentioned issues, whether environmental or due to rougher handling, it may need to be replaced, as retained moisture or a rapidly aging sensor body would no longer be reliable. Additionally, an analog sensor relies on three things to function accurately: the sensor resistance, temperature of the outbreak, and the surrounding environmental conditions. If an analog sensor is set up without the predicted values of each being taken into account, there is a high likelihood that the sensor will report incorrect values back to you, ultimately triggering false alarms. Which is very inconvenient when you need a reliable safety measure for industries that are usually outdoors, in sunny, salty, or wet climates. At times, needing to fit around tight-cornered spaces. And on what lives, property, and communities rely on for its accuracy and timely functioning. Lastly, we'll be talking about the fiber optic sensor, with components mainly consisting of a light source, optical fiber, a sensing element, and a detector. This fiber optic sensor application has quite a few benefits in the industrial space today, mainly being its high tolerance for extreme temperatures, its real-time monitoring capability, as well as its temperature positioning capabilities. But even with all the benefits offered, there are some things to take note of when looking to utilize the sensor type. One concern being that even though it is resistant against extreme temperatures, it's not so resistant when it comes to any sort of real movement or friction. Meaning that if the sensor is in an environment where there is too much vibration, the sensor angle is too acute, or, like in many cases we've seen, the sensor is being uninstalled and reinstalled for cleaning, the sensor will likely snap. Additionally, fiber optic sensors are preset in length, meaning if you need a customized length, you're out of luck. So then, what do you do when you need a specific length such as 80 meters, but the closest you can get to the needed amount is 100 meters? Well, you'll just have to use the 100-meter sensor, and in doing so, having to put the extra slack somewhere. But what does that mean in application? It means that a fiber optic sensor needs to be laid out evenly for its temperature positioning to make sense in the physical world in practical terms. So when an alarm is set off and staff goes out only to find the sensor not evenly laid out, and the hot spot detected is lost in too much sensor length, it can get pretty confusing to track where the hot spot is coming from. And with these sensor types, even fire zoning gets tricky, because customized lengths are not possible. Fire zoning is just as inconvenient to navigate and even more confusing in most cases, as the fire zone is usually needed in narrow, blocked off, or multi-floored areas. Meaning that each fire zone has another element of complexity to consider with these specific sensors, as the area around these sensors need regular maintenance, such as cable trays and the cables these sensors lay atop of. But being uninstalled and reinstalled for cleaning in many cases results in a sensor break due to the fiber optic sensor's fragile body. So with that, I'm sure you're inclined to think long and hard about what sensor type better suits your industry application, and are fully aware of the major benefits and downfalls of each, as safety is the aim, and being ill-equipped to reliably react to an outbreak isn't a game worth playing.